Happy evening to all gathered here to the 5 days online faculty development program on research methodology and data analysis for faculty and research scholars, organized by Department of Computer Science and Computer Application in association with IQAC. It's my pleasure to welcome all the participants for the 5 days online FTP program. Before we start our session, I would request the gathering to mute your audio. A day without prayer is a day without blessing, and a life without prayer is a life without power. Let's start with prayer. Now I call upon Mrs. Fabila Dani of Department of Computer Application for prayer.
Thank you, ma'am. Let's pray. Loving Heavenly Father, we come to you this hour asking for your blessings and help as we are connected together virtually in this first day of the faculty development program. Lord, grant your blessings on our chairman, Reverend Father Dr. J.E. Arulraj, our administrator, Reverend Sister A. Malajodi, our principal, Dr. R. Ruben, today's resource person, Professor C.M.T. Karthikeyan, and on all our faculty members who are connected here. We pray that this FTP should enrich our knowledge and it should be informative to all of us. We give this FTP into your mighty hands and we ask this in the name of our Lord Jesus Christ. Amen.
I request the gathering to unmute your video for a photo session. I repeat, I request all the gatherings to unmute your video for photo session. Thank you all. Kindly mute your video. Every thought you produce, anything you say, any action you do, it bears your signature. Now I request Dr. Tangama Enchi, Department of Computer Science, to give an welcome address.
Good evening to all present here. It gives me great pleasure to welcome you all for the 5 days online development program, research methodology and data analysis. I would like to take this opportunity to extend a warm welcome to our founder father, Dr. J. Arulraj, energetic principal, Dr. Ruben sir, Reverend Administrator and media faculties and students from various institutions. Now, I would like to welcome our resource person, Mr. C.M. Karthikeyan, Assistant Professor, Department of Computer Science, Government College of Engineering, Bargur, Krishnagiri. He has more than 15 years of teaching experience. He worked as an assistant professor at SRM University for 6 years and currently he is working as an assistant professor at Government College of Engineering, Bargur. He has organized 3 national conferences, 2 workshops and webinar. He has also attended various online FTP programs and webinars. We welcome you once again, sir. Thank you.
Thank you, ma'am. Everything is theoretically impossible until it is done. Now, I call upon our today's resource person, Professor CMT Karthikeyan, Assistant Professor in Computer Science, Government College of Engineering, Barkur, in the topic Mathematical Applications in Cryptography. Sir?
Yes, ma'am. Shall I start?
Yes, sir, you can start, sir.
Yes, madam. Thank you.
Thank you, sir.
Yeah, hope my screen is visible to everyone. Am I audible to everyone?
Yes, sir.
Yeah. So first, I'm very much thankful to the management of St. Joseph College of Arts and Science for giving me the opportunity to take this session. Okay, so my agenda is to go like this. That is, we are going to discuss about what are the applications of mathematics in cryptography, right? Can anyone, have you heard about the term called as cryptography? What is that? What is cryptography? Where do we need this cryptography? Cryptography plays a vital role in which of the areas? Yeah, can anyone answer?
For encryption, sir.
Yes?
Security, encryption.
Yeah, very good. Yeah, these are the few terms related with encryption, decryption, and obviously security comes into a picture when we are talking about encryption and decryption. Okay, actually there is a broader term called as cryptology is there. Above cryptography, we have a term called as cryptology. Cryptology is a combination of cryptography and cryptanalysis. Okay, then first we'll know what is cryptography. What is cryptography all about? What is cryptography? Okay, let me tell you. Cryptography is nothing but the study of various encryption and decryption techniques. That's it. So what encryption and decryption techniques is going to do is, it is going to ensure that there is a secured communication happen between two parties, or the secured communication happen between the sender and receiver, that ensures that no one has read the messages exchanged between those two parties. Okay, that is the study of cryptography. So it is having various different techniques of encryption and decryption. Then their question arises, what is encryption and what do you mean by decryption? What is encryption? What is encryption?
Let's convert plain text to ciphertext, sir.
Yeah. So this is very technical term. Plain text to ciphertext are simply a message into a scrambled message. Converting the normal message, whatever the message we are sending it, that will be converted into the scrambled message. That message cannot be read by the third party or hacker or attacker. Okay. Whereas, so this is the encryption here will be performed by the sender, whereas decryption will be performed by the receiver. Decryption is nothing but the reverse process of an encryption. Okay, so that is getting back to our original message. How the sender has sent, in the same way the receiver has to receive. So receiver, what he will do? He will decrypt the encrypted text. So he will convert that scrambled message into an unscrambled message to read actually what exactly the sender has sent. Okay, this is simply an encryption and decryption. Encryption is the process of converting a plain text to cipher text, and the decryption is the process of converting cipher text to the plain text or the original message. Okay, so that is a cryptography. Why we need to give more importance to security?
Because of lot of hackers are there, no?
Yeah, can you give some real-time example where the security needs more important, and why we need to give more importance to the security? Yes, please. So I think we have been using the ATMs, right, for our cash transactions. Okay, right. So in few years back, what will happen is, if you are not taking the money from the cash tray, what will happen? The cash tray will be closed, right? Will be closed back in the few years back, some 10 to 15 years back. Okay, what is the case, or what is the scenario nowadays in the ATM machines? What is the scenario?
Sir, sorry for the interruption, sir.
Yeah.
Your screen is not moving, sir.
No. I'm not taking. I'm just talking alone. I have not moved any slides. Slides. Just I'm giving on an introductory speech alone.
Sure. Okay, sir. Thank you, sir.
Yeah. So my question is, a few years back, the cash tray will open, right? We'll take the unless we take the money. Okay. If you take out the money, it will the cash tray will be closed, right? Okay. What is the scenario nowadays in the ATM machines? Whether the cash tray will be closed automatically, or it will still open? Yeah.
Through the ATM card.
Yes. No. I'm not talking about OTP generation and all. I'm talking about while withdrawing the money from the ATM machine, the cash tray will come, right, with the cash we need. For example, if you have put some 2,000 rupees, then 2,000 rupees will come with the tray opened. Okay, right? Once we have, if you are taking or not, what will happen? In the few years back, for a particular time delay alone, it will wait. Apart from that, what will happen? It will close it. If you are not taking the money, the cash tray will be closed automatically in the earlier days. That is some 15 to 20 years, 10 to 15 years back. Now, the cash tray will be open as it is. It won't close if you are not taking the entire money. Why they have made it like this now? That is my question. Will be waiting for some period of times, or if you are given some delay, what will happen? Automatically the cash tray will go back. Go back means it will be closed. Okay, now it is not so. It will be opened until you're taking the entire amount. Why they have made like that now? What flaws or what financial losses the banks have faced in the previous scenario? Can anyone tell me? There is an interesting fact in this. Because, for example, so for some delay, after some delay, what was happened in the few years back? The cash tray will be closed, right? For example, I have asked for 5,000 rupees to take to withdraw an amount, right? Yes. I have in the earlier days, what is the scenario is, I have trying to withdraw amount of rupees 5,000. Okay, cash tray comes with 5,000. What I do is, I just took some 3,000 rupees alone. 3,000 rupees alone. Okay, I'll put it in my pocket. What machine will assume that I have not taken the money? I have not taken the money. Then the cashier will be closing back. What will happen? My entire 5,000 balance is getting credited back to my account. But what I have done, I have taken a part of money from that. Yes? Is it clear? So that was the previous scenario. Right? Okay. So that is why they have not closed that cash tray nowadays in the ATM machines. That is the security concern in that in those years. So they have identified many financial laws across the countries in various banks. Then they have identified that the people handle the machines like that. They have taken the part of the money, leaving the tray for a delay. What the machines assumes that the person has not taken the money. Then it is getting closed, the tray is getting closed. Then that 5,000 will be credited back to the account holder himself or herself, though he has taken the 3,000 out of it. Okay, so who is the absolute loser? Banks are the absolute losers. Okay, then only they have decided not to close the tray until the person who is coming to the ATM machine for withdrawing the money, right? So that is why. So if there is any simple security lapse, there would be a huge financial losses you can face it, right? Okay. So this there are encryption, decryption started very earlier. So in case of cryptography, there is two way of categorizing: classical encryption, decryption techniques, and the modern encryption and decryption techniques. Okay, classical encryption and decryption techniques used only for alphabets, because in the earlier days the confidential matters are exchanged with letters alone. There are no numbers. They didn't use much. Okay, so in the earlier classical encryption and decryption techniques fully dependent on only the alphabets, whereas in modern encryption and decryption techniques like DES, AES, DES is nothing but data encryption standard, and then AES, advanced encryption standard, that includes every character what we are trying to exchange between the sender and receiver. So that is why it is a modern encryption techniques. Okay, classical encryption techniques we are going to see one by one now. But for all together, irrespective of classical encryption, decryption techniques or modern encryption, decryption techniques, the mathematical applications play a vital role, especially the number theory. Number theory plays vital role in the world or in the area of cryptography. Okay. Yes, my next slide is visible.
Yes, sir. Yes, sir.
Yeah. So this is so now we are going to discuss about the classical encryption and decryption techniques. In the classical encryption and decryption techniques, there are two broad categories. One is a substitution method, substitution ciphers, and the second one is called as a transposition cipher. First, we should know what do you mean by substitution. Substitution means, as the name implies, each letter symbols in the plain text will be replaced with some other letter symbol in the cipher text. Okay, so we'll be getting different cipher text from the plain text. What we have, for example, ABC is my plain text. What I can give is XYZ, which means that A is getting replaced with X, B is replaced with Z, and Y. Z replaces C, right? So that is nothing but a substitution, which means that I am substituting one symbol for the other. That is why it is called as a substitution. Whereas transposition, what do you mean by transposition? Transposition means rearrangement. Okay, rearrangement of a cipher. For example, I'm using an ABC. AB is the plain text. ABC is the plain text means I can get my ciphertext as CBA or BAC or BCA or ACB. Okay, that is nothing but a transposition, which means that with the symbols present in the plain text, I have to rearrange it into some other combination, which means that I need to use, for example, my plain text contains only 5 characters of 5 alphabets, means within that 5 alphabets, I have to rearrange it so that I can form a new ciphertext. That is why it is called as a transposition cipher. Okay, first one is in substitution, which means I'm going to introduce a totally new different symbol for the existing symbol in the plain text. Whereas in transposition, I'm going to use the same set of cipher, same set of symbols what is present in the plain text, but I'm going to rearrange it in a manner so that it cannot be identified by the attacker. That's what I have given you an example. ABC means ABC. With the substitution cipher, what could be the ciphertext? XYZ. Totally different symbol compared to the plain text. You take the same plain text with the help of a transposition. What is the concept? ABC means I can get the ciphertext either as CAB or BAC or BCA or ACB, something like that. Got it? That is the main difference between substitution method and transposition method. Under substitution, the very first cipher is called as a Caesar cipher. Caesar cipher is our first method. This is called as an oldest substitution cipher. It was used by the Julius Caesar for exchanging the messages relevant with their military affairs. Okay, you can see an example. Meet me after the toga party is our plain text. What is the ciphertext is PHHW, PHDAWHU, like that it is going. So what is the relationship between the plain text and ciphertext? Can anyone tell me? What is the relationship between the plain text and ciphertext? Yes, please. I think, am I audible?
Yes, sir. Yes, sir.
Yeah. Can anyone tell me what is the relationship between plain text and the ciphertext? You can take this meet. For the plain text meet, we are getting PHHW. What is that? So that is the every third character is replaced, right? Every third character is replaced with the character in the plain text. Okay, M, N, O, P, E, F, G, H. Okay, for T, it is U, V, W. Every third character is converted as the ciphertext. Okay, what could be the decryption? What could be the decryption for this? So for there is an encryption concept, there should be a decryption. Okay. For simple example, I can say is, for example, I am using a plus operation for an encryption. What could be the decryption process? Decryption and encryption are the reverses of one another. Right? If I am using a plus symbol for encryption, what could be the symbol for decryption? It should be obviously minus, correct? I am adding plus 3. Plus 3 for every character in the plain text. Okay. Then what will happen? You will be getting every third character in the ciphertext. For example, I want to get the my plain text back. What I should do? I should subtract 3 from my ciphertext. Okay. Then I'll get back my plain text. So encryption and decryption are the reverses of one another. So this is this general notation. Plain text would be in lower case, ciphertext will be in upper case, and key will be in italicized lowercase. Okay. Every encryption and decryption involves the key. Yeah. So this is an Caesar cipher arrangement. The entire Caesar cipher and the substitution ciphers work based on the modulo 26, arithmetic modulo 26. So this is the generalized Caesar cipher formula. C equal to encryption of plain text equal to P plus K mod 26. In the previous slide, we have seen one example. What is the key there? The key size is 3 because every third character is getting replaced. Every third character was replaced with the plain character in the plain text. So key size is 3. It is not necessary if you want to make the ciphertext as complex as possible, you can increase the key size. That will give the challenging ciphertext for the attackers to deduce it. At least she or he may identify it, but it will take much time. So this is the general procedure you need to remember. How complex you devise your key, that complex of ciphertext you will be getting it. Then obviously it will be very difficult for the hackers or attackers to deduce the ciphertext. At least it will take some time, more time to deduce the original plain text and the key. Once the key is compromised, nothing can be done. What are the messages we are exchanging between the sender and receiver will be readily read by the third person. Okay, so that is why we need to make or we need to assign the key as complex as possible. Okay, so now we'll come to this. This is the generalized Caesar cipher. C equal to P plus K mod 26. C refers to the ciphertext. Okay, P plus K mod 26. If you want to get back your plain text, what is the input? P is the plain text, this is the output. Input is C, that is ciphertext, minus K mod 26. Okay. So next is in cryptanalysis of Caesar cipher. Yeah, I have while we are discussing about cryptology, I have used two terms called as in cryptography and cryptanalysis. Cryptography is we have discussed that. That is nothing but study of various encryption and decryption techniques. What about cryptanalysis? Cryptanalysis tells us how strong our algorithm is. Okay, how weaker our algorithm is. It will tell or it will test the strengthness of our algorithm. How far your algorithm will sustain. How much time your algorithm will sustain. Whether it would take very less time to break your code or it will take more time to break our code. Okay, to check that only we are using a term called as a cryptanalysis, or nothing but identifying or finding the traffic patterns. Based on the traffic pattern, only the traffic patterns can be captured by the attacker. That is, only the ciphertext can only be captured by the attacker. He or she has to work on the ciphertext. If your algorithm is too weak, is a cipher. It is having only 26 possible ciphers. So brute force search itself enough. That is what you mean by brute force search. Just the trial and error method. Just shifting the letters one by one. For example, I can try whether he has replaced one character whether he has shifted one character or shifted 2 characters or shifted 3 characters and so on. Because maximum how many letters we have? Only 26 letters. I can check it out very easily. I can deduce the plain text very easily with the help of the ciphertext what I am having it in my hand. Okay, so it is very easy to break the ciphertext in the case of an Caesar cipher, since it handles only the 26 alphabets. Since the entire algorithm or entire technique works only on the 26 alphabets. Okay, for example, kindly break the ciphertext and tell me the answer. What could be the plain text for this? So trial and error method means you need to shift one character before, 2 characters before, like that. This is deciphering or decrypting. Decrypting means we are subtracting it. Subtracting it means it will go 1 character before, 2 characters before and 3 characters before until you find a meaningful message. How long you need to repeat this? Until you find a meaningful message. Okay, can anyone tell me what is that? What is the corresponding plain text? Yeah, can anyone try? Okay. Can anyone tell me what is that? Have anyone tried that? Can anyone try this? How to break the ciphertext? Yes? Can anyone break the ciphertext called as GCU, A, BQ, DT, GCM? How you can break the ciphertext? You need to decrypt it, right? Yes, audience, please respond. Yeah, you can see it there. Easy to break. That is, what is the key? Key is 2. Key is 2. That is, with the shift of key, you can find the plain text called as an easy to break. G minus 2. What is G minus 2? G minus 2 is E. C minus 2 is A. That is, C is 2. 2 minus 2 is 0. 0 corresponds to the letter A. U. Similarly, what is U? U minus 2 will give S. A means it will come back to Z and Y. Previous letter to A is Z and previous to Z is Y. So it is coming as EC. So for the decrypted, I have some network issues from my end. Sorry for that. Are you able to follow it?
Yes, sir.
Yes. Okay. Yeah, next is an monoalphabetic ciphers. What is monoalphabetic cipher is it is, we can say that it is somewhat the improved version of an Caesar cipher. Improved version of an Caesar cipher. Why? Because there won't be any relation. Because in the Caesar cipher, it is otherwise known as a shift cipher. Why it is can be shift cipher means ciphertext will be having the symbols shifted after 3 times or after 5 times like that. So that is why Caesar cipher is otherwise known as shift cipher. There will be a constant relationship. There is a 5 shifts means it will follow the 5 shifts for the entire plain text. Okay. Once you have found out that shifts, you can easily find out the entire original message. Okay. So in order to overcome that, they have found out then one more cipher called as a monoalphabetic cipher. Monoalphabetic cipher is, as the name implies, there won't be any relationship between the plain text to ciphertext. You can map any symbol to any symbol to the ciphertext. For example, if a single symbol in the ciphertext may be mapped to different symbol in the ciphertext. The second symbol in the plain text may be mapped to very different symbol in the ciphertext. For example, I can ABC is the plain text. I can map A to Z, B to D, C to U. Okay, so there is no constant number of shifts as we are finding it in a Caesar cipher. Okay, do you feel that still this cipher is secure? Do you feel that still it is secure? Monoalphabetic cipher will be secure? Yes. That is, you can very well claim that it is better version of a Caesar cipher because we can find a constant relationship between the plain text and ciphertext in Caesar cipher. Whereas in monoalphabetic cipher, you are mapping each symbol in the plain text to different symbols in the ciphertext. A will be mapped to some Y, B will be mapped to some F, C will be mapped to some T. Okay, there won't be any standard relationship. But still, it is also vulnerable to attack. Why? Because of an language characteristics. Okay, language characteristics, still it is vulnerable. Monoalphabetic cipher is vulnerable. So we are assigning the symbols arbitrarily or randomly in the ciphertext. Still it is vulnerable or weak because of its language characteristics. Okay. So now we have total of 26 factorial keys. With so many keys, might think is secure? Obviously no. So we may have total of 26 factorial of keys, but still it is not secure because of its language characteristics. Language characteristics means what is the language used? English language, because human languages are redundant. In the English letter, the most frequently used letter is E. Most frequently used letter is E. Okay. While looking at the ciphertext, if any of the letters are getting repeated, for example, X is coming in the ciphertext, you can assume that letter could be E in the plain text. Then you can substitute and start guessing. Then what all the words will come with E? D, these, they, something like that. We need to find out the prefix and postfix characters. Okay. By that, you need to identify which of the other character will be frequently used. Followed by E is TRNIOAS. Okay. So, for example, what should be our start guessing? By having the ciphertext in hand. If any of the ciphertext symbols are getting repeated, we need to assume that character could be E in the plain text. Then you need to find out manually what are all the combinations you can form using the letter E. You need to use the prefix and suffix characters. D. For example, you have found out E means you can check like this. These, they, something like that. Okay, then you need to go for next frequently occurring character. That is After E, it is TRNIOAS. Like that, by having the ciphertext in hand, the hackers or attackers can still deduce our plain text. Okay. So we can have a tables like a two-letter table, that is single, double, triple letter frequencies. 2-letter table, 3-letter tables, and 4-letter tables. By that, we can easily find out the ciphertext. Okay. So this is the English letter frequencies that we have seen in the previous slide. E is the most frequently used letter, followed by T, right? Then A, like that it is going, or N, S. Okay. So this, why it is mono-alphabetic cipher means every symbol will be mapped to one symbol randomly. Okay. But if the symbol is getting repeated in the plain text, you have to use the same, you have to replace with the same symbol in the ciphertext. For example, I'm using A, I'm mapping A to X. Then wherever A is coming in the plain text, you have to replace with X. That you cannot do anything with that. Okay. What is the difference between Caesar cipher and mono-alphabetic cipher is every symbol will be mapped to totally different symbols. That you cannot find any constant relationship between the plain text and ciphertext, but you can still find out the original plain text due to the language characteristics. Okay, that is our English language. By that, the hackers can identify it. So then they have come for an Playfair cipher. Playfair cipher is nothing but what it is going to do is, it is going to encrypt, or I can say that it is the first polyalphabetic cipher. So far, every Caesar cipher and mono-alphabetic cipher is getting encrypted and decrypted by letter. For example, 5 letters in a plain text means each letter will be processed individually. Okay. One by one, every letter in the plain text will be processed into ciphertext, and every letter in the ciphertext will be processed individually to convert back to the plain text. Okay, so there are the disadvantages in those ciphers. Then they have found out the first polyalphabetic cipher called as a Playfair cipher. Why it is called as a first polyalphabetic cipher means here the letters are encrypted or decrypted by taking 2 letters at a time. 2 letters. So if the plain text contains some 8 characters, then how it will be processed means every 2 characters will be processed at a time. Okay, how many times it will be processed? 4 times it will be processed. Your encryption process involves, encryption process takes 4 times. Decryption process also takes 4 times. If it is a 16 characters, then 8 times. Encryption 8 times and decryption 8 times. That is, here the plain text will be processed as 2 characters at a time. Right? It was invented by Charles Wheatstone. It uses a 5x5 matrix. It uses a 5x5 matrix. You can ask why we are having 26 letters of an alphabet, but 5x5 matrix means 25 characters alone is coming. They have given I and J in a single cell. I and J occupy the same cell. Either I or J we can use, that occupies a single cell. So it is totally an 5x5 matrix or 25 letters. Okay. Here the keyword will be given. So for example, keyword is given as monarchy. So how we need to arrange is, we need to arrange the given key across the 5x5 matrix, and we need to left out the repeated letters that are found in the key, and we need to fill in the rest of the matrix with the missing letters. Okay. For example, monarchy, first we have to fill in it. Start filling in the 5x5 matrix. MONARCHY. Okay. Then out of key matrix, what all the missing characters are there? We need to fill it in the rest of the matrices. For example, monarchy, A is already present. So you should not fill the remaining cells with A. So what are the thing? B. Then C, can we fill the C? No, because C is part of the keyword. C won't be filled, that is D. Then E is not there, E, F, G, H is already come. H is the part of an, H is then part of an keyword. Sorry. H is a part of a keyword. So that is why H is not the part, H is not filled. Then IJ occupies the same cell. Okay, either I you can use or J you can use it. Then K, L, M won't be picked up here because M is already the part of a keyword. Then N won't be filled up because it is also the part of the keyword. And O is also not filled up because O is a part of the keyword. The next P, Q, R won't be filled, R is part of the keyword. Then S, T, U, V, W, X, Z, because Y is already present in the keyword. So you have to, so while you are filling the 5 by 5 matrix, your last cell should be always filled with Z. If Z is not part of the keyword. Okay, here Z is not part of the keyword, so it is ending up with the Z correctly. Otherwise, we need to check it up whether we have filled the keyword in the key matrix correctly or not. Okay, once again I'll repeat how to fill the key matrix. Key matrix, we need to start filling our keyword. Start filling the keyword in the 5 by 5 matrix. If any of the letters are getting repeated, we have to fill it once. Okay, then the remaining letters, the letters which are not present in the keyword should be filled in other cells. Okay, that is the procedure for filling the 5 by 5 key matrix. Then this is encryption. So I have told you, so the encryption has to be done pairwise or 2 characters at a time. Okay, if a pair is repeated letter, so same letter should not be paired. For example, LL should not be paired, OO should not be paired. If that situation is coming, you need to use a filler in between those repeating characters. For example, they have given, if pair is repeated letter, insert a filler like X. Balloon, we can pair BA. You cannot pair LL. So you fill, you can include or insert filler in between these 2 characters, LX, LO, OL. Like that you have to fill it. Okay, then if both the letters fall in the same row, replace each with each letter to the right. AR encrypts to RM. If both letters, for example, they are giving an encryption called as an AR. You can see here. AR is coming, right? AR is coming in the same row. So we need to take the next character. Okay, AR means what is the next character to A? It is R. For R, it is M. So that is the ciphertext for the pair called as an AR. Okay, for encrypted, for plain text AR, the encrypted text is RM. Is it clear? If the letters are falling in the same row, what you need to do is, you need to replace with the letter next to it. That's it. Now, for an example, AR is the letter, AR is the pair of letters found in the plain text. What is the ciphertext? We can write it is, what is the letter next to A? It is R. What is the letter next to R? It is M. You need to come back to the beginning of the row. Okay, so RM. For example, if I am giving ON means ON is falling in the same row. What is the encrypted text? NA, correct? For O it is N, for N it is A. So NA is the encrypted text or ciphertext. Similarly, for the column also the same. If the 2 characters are falling in the same column, you need to take the character next to it. Okay, if it is of the last character, it will come to the top of that particular column. We can see here MU. If both letters fall in the same column, MU encrypts to CM. You can see MU, right? What is the next character to M? It is C. What is the next character to U? It is M. So for MU, it is CM. CM is the ciphertext. Is it clear? You are finding, looking at the pair of characters in the plain text. If it is falling in the same column or same row, we need to take the character next to it. If it is in the row, you have to see it across the row. If it is in the column, you need to see across the column. We need to take the next character across the row or column. Okay, according to the characters falling. Okay, for MU it is CM. Okay, so if not the above, if any of the, if it is in the neither the column nor the row, if the two characters are neither in the column nor in the row, means what we need to do? Each letter is replaced by the one in its row in the column of the other letter of the pair. For example, HS. HS we need to encrypt. HS. H is in one column, S is in another column. So that, which means that it is in the diagonal position, correct? Okay. Yeah, what is that? HS means what we need to do it. What is the corresponding encrypted text? We need to take BP, right? HS encrypts to BP. You can see here HS. We need to take the corresponding opposite diagonal to HS. HS means simple way is you need to take the opposite diagonal for that, for those characters. It is in the diagonal, no HS. Take the opposite diagonal of that. It is BP. Okay. Is it clear? This is how you need to do if it is falling neither in the row nor in the column. Okay. So, okay, I'll rather than going into this thing, I can skip some of the slides. Let me come to discuss about the important topics in the mathematics. We'll see that. Yeah, let us come into one. Prime numbers, right? Prime numbers. So I am skipping because it will take more time. So let me get into the mathematical applications now directly. The classical encryption techniques, they have used the modulo arithmetic under 26. Arithmetic modulo under 26 they have used. Almost all classical encryption techniques uses the arithmetic modulo 26. Okay. There also they have used the mathematics. So prime numbers play a vital role in our cryptography, right? We know that what is prime number? A number which divides by itself and divisible by 1. That is nothing but a prime number. Okay. What is prime factorization? What is prime factorization? That is a number that can be expressed as a product of primes. Prime factorization of a number n is when it is written as a product of primes. For example, I can write 100. How I can write 100? 100 is not a prime number, right? 100 is not a prime number, but it is a composite number. You know that in number theory, you know that any composite number can be expressed as what? Product of primes, right? Can be expressed as product of primes. How we can express? Can anyone tell me? 100 is a composite number. How you can express as product of primes? Can anyone tell me? What is that?
Five into two.
Yeah.
Into two. A series of 5 into 2 into 2.
Yeah, that is, it is simply a 5 square into 2 square.
Yes, sir.
Yeah, 25 into 4. You cannot write 25 into 4 because 25 is not a prime number. 4 is also not a prime number. So you need to write in the integral powers of prime numbers. So 5 square into 2 square. That is the that is how you can write the prime numbers. Okay, yeah, any composite number can be expressed as a product of primes or integral powers of product of primes. That in that way we can write it. Yeah, this is a very important point. When two numbers are said to be relatively prime, can anyone tell me? When two numbers are said to be relatively prime or co-prime? Yeah? Can anyone tell me when two numbers are said to be relatively prime? Two numbers are said to be relatively prime or co-prime if their GCD is 1. For example, GCD of 7, 15. What is GCD of 7, 15? GCD of 7, 15 is 1, correct? Because you cannot find any common divisor apart from the 1. So we can say that 7 and 15 are relatively prime or co-prime. It is very more important property in prime numbers. Two numbers are said to be relatively prime or co-prime if their GCD is 1. Okay? Yeah, this is an Fermat's theorem. Fermat's theorem can be written as a power p minus 1 is congruent to 1 under modulo p, where p is the prime and GCD of a comma p equal to 1, which means that a power p minus 1 is congruent to 1 under modulo p will work if GCD of a and p is equal to 1. Otherwise, this Fermat's theorem won't satisfy. Okay? So, which means that whenever a power p minus 1 is divided by p, which leaves the remainder 1, if and only if GCD of a and p are 1. Okay, that is the Fermat's theorem. So it is also known as Fermat's little theorem that can be rewritten as a power p is congruent to a under p, which is nothing but a power p minus 1 can be written as a power p into a power minus 1. A power minus 1 can be brought down to denominator, that is a power p by a. Then cross multiplication will give this equation. A power p is congruent to a under modulo p. Okay. Yes, so here example, a equal to 7, p equal to 19. Okay, you can check it up the Fermat's theorem. First, we have to check whether GCD of a comma p is equal to 1. Yes, obviously. GCD of 7 and 19 is 1. So it is going to give a power p minus 1 is congruent to 1 under modulo p, which means that here a is 7. 7 power p minus 1. What is 7 power p minus 1? 7 power 18. Correct? 7 power 18 can be written as 7 power 16 into 7 square. How we can write 7 square? 7 square is 49. 49 mod 19. 49 mod 19 means what is the purpose of modulus operator? It is going to give the remainder when we divide two integers, right? 49 by 19. Two 19s are 38. So remainder is 11. Okay. Similarly for 7 power 4. 7 power 4, what will happen? 7 power 4, we can write it as 7 square into 7 square. So 7 square we have already found out. What is 11? 11 into 11, 121. If it is more than 19, we need to do the modulo operation. 121 mod 19. What it is giving? 7. So 7 power 4 mod 19 is 7. So like that they have found out 7 power 8, 7 power 16, like that. So 7 power 18 we need to find out, because a power p minus 1. Here a is 7, p is 19. We need to find 7 power 18. 7 power 18 can be written as 7 power 16 into 7 square. 7 power 16 is 7. 7 square is 11. So 77. 77 mod 19. 77 mod 19. What is it? 4 19s are 76. Remainder is 1. So Fermat's theorem is proved. Fermat's theorem can be satisfied if and only if, keep it in mind, if GCD of A comma P, B, P equal to 1, which means that if A and P are relatively prime or A and P are co-prime. Okay. So followed by Euler-Torsion function. This is a function to return the number of values that are relatively prime to a given number. You can see an example here. There is a formula called as phi of p. Euler-Torsion function is represented by phi. Phi of p equal to p minus 1, where p is a prime number. It will tell you the Euler-Torsion function returns the number of terms that are relatively prime to a given number. For example, phi of 37. What they are trying to find is how many values are relatively prime to 37. We have to start from 1, GCD of 1, 37, GCD of 2, 37, GCD of 3, 37, GCD of 4, 37. Relatively prime means what? Those two numbers should give the GCD is equal to 1. GCD of 1, 37 is 1, GCD of 2, 37 is 1, GCD of 3, 37 is 1, GCD of 4, 37 is 1. So it is very difficult if you are going manually. So in order to, you need to find how many terms are relatively prime to a 37, means you can find it by Euler-Torsion function. Okay, that is giving a two formulas here. Phi of p equal to p minus 1, where p is a prime number. If it is p is a prime number, you can find directly by using a term formula called as p minus 1. That is, that number of terms are relatively prime to that particular number. Phi of pq, we can write it as phi of p into phi of q. Which once again, if p is a prime, p minus 1 you can write. Similarly, q is prime, q minus 1 you can write. So now you can see here, phi of 37, 36. Because why it is 36? Because 37 is a prime number. Prime number means what is the formula? P minus 1. So 37 minus 1 is 36. Phi of 21. Now you can look at the number. 21 is not a prime number, but you can split as, or you can write as a product of primes. So 21 can be written as phi of 3 into 7. 3 is a prime, 7 is a prime. So phi of 3 into phi of 7. Phi of 3 means 2, that is 3 minus 1. Phi of 7 is 7 minus 1 is 6. So 2 into 6, 12. 12 numbers that are relatively prime to 21. You can, otherwise what you need to do? You need to do it manually. 1, 21, 1. 2, 21 is 1. But 3, 21 is GCD is 3. You should not include that. Okay. So that is the concept. 7, 21 won't come. 7 won't come because GCD of 7, 21 is 7. So Euler-Torsion function returns only the numbers which are relatively prime to a given number. Okay. Right? So using Euler-Torsion function, we have used another theorem called as an Euler's theorem, that is a power phi of n is congruent to 1 under modulo n. Once again, here a and n should be n relatively prime or co-prime. Okay. Here you can take an example. A equal to 3, n equal to 10. Phi of 10. Phi of 10, what is phi of 10? Now it is 4. Because 10 can be written as phi of 2 into 5. Phi of 2 into phi of 5. 2 is a prime number, so 2 minus 1 is 1. Then phi is a prime number, 5 minus 1 is 4. So 1 into 4 is 4. So phi of 10 is 4. Now you apply it to the formula. A power phi of n. So 3 power 4. 3 power 4 is 81. 81 mod 10 is 1. Clear? Once again, so the prime numbers and prime number properties are very important. That is, the relatively prime and co-prime properties are very important. Okay, that will help you in that is having a huge applications in RSA and Diffie element key exchange problems. These Euler torsion functions and all those things, right? So Chinese remainder theorem is simply abbreviated as CRT. So I'm not going to detail here because due to shortage of time. So what is the idea of Chinese remainder theorem is, it is used to find the unknown for the given set of equation. You need to find a single unknown for a given set of equation which satisfies all the equations. Okay, that you can find a unique solution that satisfies the given set of congruence equation. That is the aim of a Chinese remainder theorem. It is simply abbreviated as a CRT. Okay, for example, you have given a set of 3 congruence equations, right? You need to find one value that satisfies all the given equations. For example, here they have given R2 equal to 0, x mod 2 equal to 0, and R5 equal to 3, x mod 5 equal to 3. So you need to find the x. That is, when we divide x by 2, it leaves the remainder 0. When we divide the same x by 5, it leaves the remainder 3. Okay, you need to find a single x which when divided by 2, it has to give remainder 0, which when divided by 5, it has to give the remainder 3. That is the aim of an Chinese remainder theorem. It is a more interesting theorem. You can browse it through, right? I can come to one primitive root. Yeah. Primitive root, what is mean by primitive root means, you can go through this. That is, you need to find a primitive root of a particular number. If you are able to find a square, a power p minus 1 are distinct mod p, then a is called as a primitive root of p, right? Now we can try to find out primitive roots of 19. What do you mean by actually exactly a primitive root means? For example, here we are asked to find the primitive root of 19 means, if you are finding an integral powers of a under modulo p, it has to generate the values from 1 to 18, because since we are finding the primitive roots of 19, that particular number, which number is generating under the integral powers under modulo 19, in this case, it has to give 18 distinct values starting from 1 to 18, right? If you are asking to find the primitive root of 5, then you need to find a number which generates the values from 1 to 4. When we are writing the that number in the integral powers under a modulo 5, it has to generate values from 1 to 4. Then that particular number is called as a primitive root. Okay. Now we are aiming to find the primitive roots of 19. You can see here. You can see the table here. I am taking a as 1 square mod 19 1, 1 cube mod 19 1. If up to 1 power 18, it is 1, because we need to find integral powers up to p minus 1. Correct. Now you try with 2. 2 mod 19 2, 2 square mod p 19 4, 2 cube mod 19 8, 2 power 4 mod 19 16, 2 power 5 mod 19 13, right? 2 power 5 mod 19 13, 2 power 6 mod 19 7. Okay, so I have told you that the numbers has to be generated from 1 to 19, but it is not in the same order. It may be in the scrambled order. We need to ensure that all the terms started from 1 to 18 have been generated. Yes, using 2, we are able to generate the values from 1 to 18. Then we can say that 2 is the primitive root of 19. And one more point is coming. There can be more than one primitive root for a given number. It is not necessary that there should be only one primitive root for a given number. You can find more than one primitive root. You can see here by taking 3. 3 is also generating the values from 1 to 18. Then I can say that 3 is also the primitive root of 19. 10 is also the primitive root of 19 since it generates the values from 1 to 18. Clear? 13 is also the primitive root. So primitive roots of 19 means I can say 2, 3, 10, 13, 14, 15. Okay. That is, you need to take a random number. You need to find up to the integral powers under modulo p. Because primitive root, you can find it for a given prime number alone. You cannot find it for any number. You can find a primitive root. Primitive root can be found only for a prime number. Okay. So you can take any number and raise it to integral powers up to a power p minus 1 under that modulo prime number. You have to do it. If that particular number is generating up to 1 to p minus 1, then you can say that that particular number is the primitive root of a specific prime number. Here you can see here for 19, there are how many primitive roots? 6 primitive roots. 2 is generating the values from 1 to 18. When we are raising to the integral powers of 2, 2 square, 2 cube, 2 power 2 mod 19, 2 square mod 19, 2 cube mod 19, 2 power 4 19, 2 power 5 mod 19 and so on. Similarly, when I am raising the integral powers of 3, it is also generating the integral powers from 1 to 19. That is 3 mod 19, 3 square mod 19, 3 cube mod 19, 3 power 4 mod 19, 3 power 5 mod 19 and so on. By looking at, we are able to get the values from 1 to 80. Right? So that is nothing but a primitive root. Primitive root is playing a vital role in the Diffie-Hellman key exchange algorithm. If and only Diffie-Hellman key exchange algorithm will work if and only if you are getting the corresponding primitive root for a prime number, because prime numbers play the role in the Diffie-Hellman key exchange as well as the round reverse Shamir-Adleman algorithm, are simply abbreviated as an RSA algorithm. Those RSA and Diffie-Hellman key exchange algorithms are considered as an public key cryptography algorithms. Okay. Those algorithms take heavy help from the prime numbers and their properties. Okay. Let us check the private key and public key crypto systems and RSA and Diffie-Hellman key exchange, and we'll close up the session. I'll rush up now. Okay. I'll rush up now since the prime numbers and their properties are extensively used in these two algorithms, that is RSA and the Diffie-Hellman key exchange. Before that, we should know what is private key cryptography and public key cryptography. Private key cryptography means there will be only one key that will be shared between the sender and receiver. Okay. Example for private key cryptographies are cryptography algorithms are data encryption standard, advanced encryption standard, blowfish. Those cryptographic algorithms are coming under private key cryptography, since those algorithms use only one key that has to be shared between the sender and receiver for encryption and decryption. In contrast, public key cryptography uses two keys, one for encryption and the other for decryption. For encryption decryption, what is the scenario is the sender will use the receiver's public key to encrypt the message, right? For example, I want to send a message to B, right? Then the public key of B will be available openly. Then I will use the public key of B for encrypting the message that I am going to send it to B. I will encrypt the message with the public key of user B. Okay, then I will send it to user B. What user B will do is, he or she will decrypt the same message with his own private key that has not been shared even to the user E. Sender himself or herself may not know what private key is going to be used at the receiver end. Okay, so the security is very high in the case of an public key cryptography compared to an private key cryptography. Okay, right? So let us directly get into an RSA, how RSA works. RSA, it has been named after their inventors, Rivers, Shaman, Adelman. It is a widely used public key schemes, right? Let us get into an RSA setup. Okay, we need to select a large primes, two large primes random, PQ, right? Then n equal to P into Q. Then we need to find phi of n. Here you know the purpose of an Euler-Torsion function. What is the need of studying Euler-Torsion function? Here for Euler-Torsion function is used. Phi of n. Phi of n is nothing but n is nothing but P into Q. So phi of n means phi of P into Q. Phi of P into Q can be written as phi of P into phi of Q. So what is the formula? P minus 1 into Q minus 1. Correct? That is phi of n is equal to P minus 1 into Q minus 1. Then we need to select a random encryption key that lies between 1 and phi of n. For example, phi of n is coming as 10 for assumption, 10. Then encryption can be selected from 1 to 10. Okay? So that is the condition for encryption. And similarly, that encryption should be E and phi of n should be relatively prime. For example, phi of n I have told you as 10. I cannot take 5 because GCD of 5 comma 10 is 5. E and phi of n should be relatively prime. Then I can take 3 because GCD of 3 comma 10 is 1. Similarly, I can take 7. GCD of 7 comma 10 is 1. Right? You can take between 1 and phi of n, but in addition to that, E and phi of n should be relatively prime. Following that, you need to find an what? You need to find an decryption key. That is D, when we are multiplying with the D, it should give 1 under modulo phi of n. You need to find a number that should be multiplied with E. When we are dividing it with phi of n, it should leave the remainder 1. That number is called as a D. We can say as D is the multiplicative inverse of E. D will always lie between 0 and n. So encryption key, public encryption key is E comma n. Decryption key is D comma n. I repeat that decryption key. That is, we have found out E, right? We need to find another number when it is getting multiplied, and that multiplication product when it is getting divided by phi of n, it should give remainder 1. And that situation, what is the value? Apart from the E, that is considered as a D value. That is called as a decryption key. Okay? Yeah, you can see here how it is, why RSA works, because of Euler's theorem. A power phi of n mod n, where GCD of a comma n equal to 1. In RSA I have n equal to P into Q. Phi of n equal to P minus 1 into Q minus 1. Choose E and D to be the inverses mod phi of n. That is, we need to find, that's what I have told you, right? We are randomly selecting E because E should lie between 1 and phi of n, and E and phi of n should be relatively prime. Based on E, we need to find another value called as D that is considered to be an multiplicative inverse. because we know that E and encryption and decryption are the reverses of one another, right? Okay, E into D equal to 1 plus K into phi of n for some K. Then C power D equal to M power E into D. M power E into D can be replaced with 1 plus K into phi of n, right? M power 1 into, that is power can be added, right? M power into M power phi of n whole power K. Yeah. So M power n into 1 power K equal to M power n is equal to M mod n. M power 1. So that is in place of an E, what we are getting. M power 1 is what we are getting. M power 1 in place of M power E is M power 1 we are getting, right? We know that M power phi of n is nothing but mod n, that becomes 1 power K. So anything power 1 power in any power it is 1. So M power 1, which is nothing but M mod n. So that is this is called as a decryption. C power D. C power D means ciphertext. Using ciphertext, using a decryption key, I am able to get back my original message called as an M. Clear? You can try out these examples. P equal to 17, Q equal to 11, N equal to PQ means 17 into 11 is 187. Phi of n means P minus 1 into Q minus 1. P minus 1 is 17, that is 17 minus 1 16. 11 minus 1 10, 16 into 10 160. We can choose E between 1 and 160. You have huge range. Here they have selected E equal to 7. We have to compare that whether E and phi of n are relatively prime. That is, we have to check 7 and 160 are relatively prime. Yes, 7 and 160 are relatively prime. So they have selected E equal to 7. Then we have to find D using E. When we are multiplying with the E and it divided by 160, we should get a remainder as 1. That value is considered to be a D, right? We know already E is 7. Correct? Okay. When we are multiplying with 23, what I am getting is 161. 161 mod 60 is mod 160 is 1. So D value is 23. Correct? D value is 23. So public key is E comma N and private key is D comma N. Okay. And let me go through a Diffie-Hellman key exchange. So public key cryptography has 3 applications compared to a private key cryptography. Private key cryptography it is having only one application, that is we can perform only encryption and decryption. Whereas in public key cryptography we can perform encryption and decryption, we can perform a digital signature, and we can perform a key exchange. That is we can exchange the key between the sender and receiver. That is possible through a public key cryptography. That key exchange is possible through an Diffie-Hellman key exchange algorithm. Okay. So what it will do is it enables 2 users to securely exchange a key that can be used for subsequent encryption and decryption messages. Decryption of messages. This is the setup. This is the setup. So user A, sorry, excuse me. Yeah. All users agree on global parameters. So you need to take large prime integer or polynomial called as Q. Q is a prime number, and you need to find the primitive root of that prime number. What prime number you are taking, you need to take the corresponding primitive root for that number. That is, A is the primitive root of Q. Then each user generates their own key, that is their own private key. That is XCI. User A will create XCI less than Q. He has to generate his private key that should be less than the prime number they have selected. XA less than Q. Public key, how he is creating or generating his public key is represented by YA and private key is represented by XA. YA equal to A power XA mod Q. That is the public key of user A. Similarly, user B generates YB. That is, his private key is XB. XB is obviously less than Q. YB is equal to A power XB mod Q, because A is the primitive unit of Q. Correct? Each side keeps the X value secret and makes Y value public. Now you can see how the key is being exchanged, right? For example, so K equal to YB power XA mod Q. User A computes the key as K equal to YB power XA mod Q, because YB is the public key of user B, XA is the private key of user A. How user B computes? K equal to YA power XB mod Q. He uses the public key of user A and uses his own private key. Now we need to check whether it is giving the same value, whether the key has been exchanged. K equal to YB power XA mod Q. How we can write it? What is YB? YB is nothing but A power XB mod Q. You can refer to the previous slide. How public key is generated using the private key of their own, right? So YB is nothing but the public key of user B. So YB equal to A power XB mod Q whole power XA. Entire YB is getting replaced with this formula, A power XB mod Q whole power XA mod Q. Then I can write it as A power XB power XA mod Q. Simply I can simplify like this under modulo arithmetic. So A power XB XA can be written as A power XB A, correct? In the power how we can write? A square power 3, how we can write? A square power 3 can be written as A power 6, correct? In the same way, A power XB power XA can be written as A power XB XA mod Q. Now I am bringing XA inside the A and I am keeping XB outside. So A power XA XB mod Q. So A power XA mod Q whole power XB mod Q. So now what is A power XA mod Q? Which is nothing but the public key of user A. So YA X power B mod Q, which means that both the key are same. So from the one, the other can be arrived. So which means that A and B share the same secret key. So one more important point is, we are telling that in private key cryptography, there is only one key that is shared between the sender and receiver. How it has been achieved means through this diffie-element key exchange alone. Okay, before start exchanging their messages, key must be shared. We have not been revealed how the key has been shared. Key has been shared through this diffie-element key exchange, or they are using a public key with the help of a public key cryptography. They are exchanging it. Then they are performing an encryption and decryption process. Okay, I think I'll stop with this. I can talk time. I will take much of time to talk about that. Still, I have missed out many topics in that, so I have to rush up due to the limited time. Hope the people have understood concept to some extent. I cannot expect the thorough understanding from 1.5 hours session. I assume that some of the concepts you have got it. Thank you, sir. Thank you, ma'am, for the opportunity given to me. Over to you.
Thank you, sir. No duty is more urgent than the talk written in thanks. Now, I call upon Dr. N.G. Tangama of Computer Science Department to deliver a vote of thanks.
I would like to express my gratitude to all esteemed delegates of the webinar for their presence and contribution to make this webinar a great success. I extend my gratitude to our Honorable Chief Guest, Mr. C.N. Karthikeyan, to take out the time from his busy schedule to grace this event. I also thank all the staff members from various institutions. And finally, I thank the technical team for the great support to organize this event in a successful manner. Once again, I thank you all. Thank you, sir.
Thank you, sir. Sir, thank you very much, sir. We have a lot of positive comments in this chat box, sir. Thank you very much for your wonderful insight.
Thank you, sir.
So you can leave, sir. You can
Okay.
leave now, sir.
Thank you
very
so
much,
much.
sir.
Thank you so much.
Participants, kindly fill the feedback form. Once you fill the feedback form, you can leave the meeting. We'll join by tomorrow.
Jennifer